So we've seen yesterday that the phase that I read out here, the atomic phase of the left interferometer and the one on the right one, it depends on the phase written on the atoms in 4 points here, and for right the 4 points on the other one. Now the phase that I write here depends by the phase of this laser minus the phase of that laser. This is what I showed yesterday. Okay? So if you consider a single interferometer, so the gravimeter, you will have that the phase noise imprints a lot of acceleration noise. It's like the noise of the mirror. So you have a shaky ruler in some way. So this ruler on this side is shaky, but it acts in exactly the same way on the two, because it's the photon emitted at the same time here, so with the same noise, that interacts first with the cloud on the left and then later time with the photon with the atoms on the right. That's not the case of the photon coming from the right side, because the photon that closes the two photon transition here for atom on the left has been emitted at this time, while for atom on the right it has been emitted at a later time. Okay, so you see that there is a problem. We'll see it later, because here you imprint a lot of phase noise. If the laser is not, well, even if it is hyper stable, you imprint noise because you want to see gravitational waves, so they are really small. Okay, can I go back there? So that's a configuration. It's a gravity gradiometer, essentially. We have two different interferometers, and we want to measure the phase difference between the two. So I was saying that the atoms, in some way, they act as the mirror for LIGO. Okay, so they have to read out the phase of these optical links, more precisely of the optical links coming from the right, because the left is a common mode. So this is a pretty important point, because it's one of the fundamental differences between atomic interferometers and optical interferometers. Optical interferometers are limited by the quantum projection noise of photons, so of the light, while atom interferometers are not. Even if you use the effect of the gravitational wave on the optical link, we'll see later, the limitation is set by the capability of read out the phase imprinted on the atomic ensemble. So we are limited by the quantum projection noise of the atoms. Okay, atoms here and atoms there. So in order to improve the sensitivity of the device, we have to increase the number of atoms, for example, on one side and the other, or to apply techniques in order to boost the sensitivity. What we were saying yesterday, going from 1 milliradian down to 10⁻⁴, 10⁻⁵, or more. Here I explain the configuration. The control is the one that sets the pulses, and the other one is always on. The gravitational waves signal come from the effective timing of the passive laser, and here I have some easy calculation. So consider the emission of the photon at time 0 that determines the splitting of the atom on the left side at a time that is x1 in this case. Okay, we consider h and c equal to 1. So now to see the emission time tau a1, we have to take twice this time. Show it here. So that's the time when the splitting happens. To determine that one, I just double that time. So I take it here, and then I go back in time by L with C and H equal to 1. Okay. So light is emitted from the left laser at time 2x1 minus L. Now, if there is strain for the H because of gravitational wave, we have that x1 goes to x1 multiplied by 1 plus h, and also the other one is multiplied by 1 plus h. This means an extra phase hk 2x1 minus L. It's just simple math there. And so now you bring x1 to 0 and x2 to L, just for simplicity, and you get that the phase should be proportional to the product of h, k, and L. Okay? And what is important is that if you make the full treatment, analytical treatment, you get more or less the same result. The exact formula is more this one, but you have K, H, and L, and then you have other terms that depends from the phase of the gravitational wave at the time that you run this probing, and then there is one part that depends from the sensitivity function of the interferometer. So I will not really explain the math that gives this formula, but I will try to explain why we get this strange sensitivity function for the gravitational wave detector. So this formula translates into this graph. Okay, there are several features that I will explain. Yep.
Is this like a transfer function of the instrument, or is this actually...
That's the sensitivity.
Well, I'm trying to ask what you mean by sensitivity. Do you mean the noise level in the instrument, or do you mean the transfer function between strain and...
So here I consider a signal-to-noise ratio of 1 for the sensitivity. So I consider to detect a gravitational wave with a signal-to-noise ratio of 1. I don't know if it is what is commonly adopted as
Yeah, John actually uses the response function, but go ahead.
okay. So the several features I want to discuss is well, the fact that at really low frequency we lose sensitivity, the level that we reach, why there is some sort of boundary at high frequency, and then these strange features. So several peaks of sensitivity and several notches. Okay. So the configuration that was considered in the first of these two papers is a distance between the two interferometers of 1 kilometer, an interrogation time, so the distance between successive pulses of 1 second, that gives as a target high sensitivity 1 Hz of the order of bar 2 pi. Large momentum splitting of 100 h bar k, and then a 10 to minus 5 per square root of hertz sensitivity for the interferometer, which can be obtained, for example, for 10 to the 6 atoms, which gives 10 to the minus 3, and 20 dB of squeezing. So, for what concerns the low frequency, you can imagine that if you have a gravitational wave that is much longer in terms of period with respect to the probing time of the interferometer, sensitivity goes down, and it happens that it goes down like omega square. And this is the response function. Okay. Okay. And so it goes down like omega square. Second point is how it's possible to get to 10 to minus 17 per square root of hertz. So as I said, they consider 10 to minus 5 square root of hertz sensitivity. This is proportional to the signal, as I said before, HKL. And if you just isolate H, you obtain this value. So 10 to minus 17 per square root of hertz. And now the strange features, so the maxima and the notches, to understand why they occur, just consider that the phase that you measure on one of the two interferometers is given, as we explained yesterday, by this formula. So phi, the phase imprinted in point A, minus phase in B, plus phase in D, minus phase in C. Essentially, the difference of phase between successive pulses. Okay? So now, if you have a gravitational wave that is at maximum in A, minimum in B and C, and maximum again in D, you clearly see that you detect the maximum signal. And this happens not only for this configuration, so for this period of the gravitational wave, but for any time you have an odd number of periods in the 2T. For example, when you have 3 or 5 or 7 period in 2T time. Okay? The opposite happens if you have an integer number of periods in T interval, because now when you sense this wiggling, you are always at the same position. Okay? And this explains the notches when you have 2 periods, 4 periods, and so on. So now if we consider the the sensitivity that we have at the maximum point, so it's always the same. If we concentrate for a while to the second one, we have that here we have 3 periods during the total interrogation time, and in some way we are wasting the fast wiggling of the gravitational wave, because we just probe here and there and there. The group in Stanford proposed to exploit this fast oscillation of the gravitational wave, and instead of using a single loop interferometer on each side, they proposed to implement a diamond configuration where by which you can probe the gravitational wave at the maxima of its evolution. And in this way they show that you can get a factor 3 in this case boost of the sensitivity. This is not exactly the same as making 3 successive interferometers separated, independent, because in that way you will get a factor square root of 3 enhancement and not a 3. And so you gain this way, making taking essentially the same atoms and coherent along all the path. So what has to be stressed is that you can go from this configuration to this configuration without changing the setup. You have just to reprogram the sequence. It's something that you do software, and send more pulses, okay, at the right time, obviously. It's something that makes this kind of experiment very versatile. In this way, the sensitivity function becomes peaked, really peaked, at a given frequency. In this case, 1/3 of the total evolution time for the interferometer. And so you go from, so here it's 10 to the minus 20, it is equivalent to 10 to the minus 17 in the other graph. So without this diamond configuration, there will be the response function going here. Using this peak configuration, they can dig and go down by 1 and even 2 orders of magnitude at very specific frequency intervals. You pay because you lose in other frequency ranges, but it can be really important if you want, for example, to follow a chirp of a signal. So now the limit set by the 2-photon configuration is what I was saying before. So to close the 2-photon transition, to have the splitting here and there, we use a laser that is common mode coming from the left, so we are not sensitive to its noise, but that's not the case for the laser coming from the right, and so we are really sensitive to the technical noise of this laser. So if this laser between here and there changes its phase because of phase noise, frequency noise, and so on, this effect will be imprinted in the interferometer here with respect to the interferometer there, and we will get a differential signal that we can interpret like a gravitational wave. The solution is to adopt a Virgo or LIGO-like configuration. So instead of making a single baseline device, make a 2 baseline cross orthogonal configuration. So now the photon are provided by 2 control lasers. These are the lasers that whose noise is common mode rejected. So this laser determine the pulses pi over 2, pi over 2, and so it gets imprinted in the same way on the 2 atomic wave function. And the same for laser control 2. Here is the passive laser, the one that is always on, and to which you are sensitive here and there, but in the same way, because you split this photon in 2, exactly like LIGO. And so in this way you can become insensitive to its effect. You then need 3 satellites or 3 labs on ground. The other solution is to use a single photon interferometry. We shortly considered them yesterday, but now we will consider them in more detail, because it's really the baseline solution nowadays for the proposal based on atom interferometry. So instead of relying on photon coming from 2 directions in order to increase its phase sensitivity, now you can use directly optical photons. So here is, for example, the level scheme of strontium, an atom that is adopted in optical clocks. And it has a lot of interesting features to cool them down, but what is interesting here is this yellow line. So indeed it's red because it's 698 nanometer, but its line width, so the line width of this line is 1 milliards estimated theoretically, because nowadays the best produced laser is 20 milliards, so it's not yet capable of really being limited by the intrinsic line width. You are limited by the line width of the laser. Anyway, it should be around 1 milliard. So this gives a lifetime for the excited state of 160 seconds. So you can use this optical transitioner to split with an optical kick, so with a big splitting and a big phase imprinting. And at the same time, you have that excited state survive for long enough. Okay? So now you have a single laser, essentially. That's the point. Instead of having the two lasers, you have a single laser, and each phase noise is put as a common mode on the two wave packet, and then is common mode rejected. Yeah. Here. So this one.
No, this curve.
Yeah.
So if I understand, I think what you've done is you've taken phase noise, which is white. It's the 10 to the minus 5 hertz phase noise.
Mm-hmm.
And then you divided that by the transfer function from strain to phase. So in other words, it's told you what the effective noise is in terms of strain rather than in terms of phase. So it's sort of white phase noise divided by the transfer function of the instrument from strain to phase.
So this is what, so typically we have an interferometer, it's 10 to minus 3, 10 to minus 4, 10 to minus 4 radian sensitivity. So you make one measurement, that's what you can measure. And then I just suppose that the signal coming from the gravitational wave is at that level.
And that's the transfer function between strain and phase.
Yeah.
So what you do is you divide
Yeah.
this thing by the
What
so
did
that
we
is a noise curve between.
Yeah, I did here. Instead of using the full formula, I just use the simplified one here. That's the signal. So now, instead of using the two photon transition, we are with a single photon transition that is intrinsically immune to laser technical noise. And now just to respond to a question of yesterday, I don't remember whom, but question was but this excited state can decay. In this case, it's not like this state that is metastable that can have a life of weeks, but it has a lifetime that is 160 seconds. So now if you make an interferometer of 0.1 second, 1 second, it's fine. But if you make an interferometer of 10 seconds, 100 seconds or more, it starts becoming annoying. Because what happens is that I put this tiny blue line here, is that atoms just decay. They go back to the ground state, and they're not anymore part of the interferometer. So what you have at the end of the day is that you will see a loss of contrast of the interferometer. You will not really move the phase, because this atom will be just lost. But so if you start making, for example, in a satellite configuration, you can see a 200 seconds interrogation time. You will have not many atoms remaining. And the solution came again in the same paper from Kazevich, and it introduces again a second laser from the other side, not to make two photon transition, because they act at a different time. So you first shine the laser from the left side, you split here, later time it splits there, so its noise is common mode, and then only when the photons of this pulse reach the satellite on the right side, a second pulse is shined from the right side on the opposite one, in order to selectively interact only with the atoms in the excited state there, because you can discriminate them because they have a different velocity, so you can Doppler select them. And you put them back in the ground state, giving an extra kick, by the way, and so you even twice, so you double the sensitivity. And you avoid, most importantly, the loss of contrast. So here I just put a long list of background noise sources that have been extensively considered in one of the initial papers of the group of Stanford. Again, and then there are several other articles that consider more explicitly single or a few of them. And so again, I consider a phase sensitivity of 10 to minus 5 radian over square root of Hertz, which gives an acceleration sensitivity, delta G over G, of 10 to minus 15 over square root of Hertz. And what they did essentially was to consider all these noise sources and try to find out the way to constrain them in order to induce an acceleration on each of the two interferometers that is less than this level. In that way, you can hope to see a gravitational wave that has that effect on the interferometers. So we can quickly read this list. So there is vibration noise. We extensively consider vibration noise before. There is a laser phase noise. You eliminate it with a single photon transition. There is Newtonian gravity noise. On ground, as we'll see, is a limiting factor. In space, you have to carefully design the satellites and everything, no moving parts and so on. There is timing errors. So a lot of rejection for several effects is based on the fact that the timing is really precisely tuned and symmetric between different parts of the interferometer. There are rotations and Coriolis, residual magnetic field. You see that typically you have to shield by magnetic field, electric field, and so on. There is a final temperature of the atomic sample. We discuss a lot about how to reduce it, delta K cooling, and so on. There are atomic collisions. As we said, we are intrinsically insensitive to vibrations, even on ground, because the atoms are in free fall. But at the launching time, the laser or the tools that you use to launch, they move, they vibrate, and so there is some effect. They can be controlled. There is the curvature of the beam used to manipulate these atoms, because if you consider a distance of kilometers, hundreds of kilometers or more, you will have a curvature that imprints momenta that are not directed along the optical link. They consider even more fancy effects like solar wind and photons, black body radiation, thermal gradients, and so on. And they did the math and they say that it's possible to constrain them below the sensitivity of the experiment. Obviously, if you increase the sensitivity, because this is done for 10 to minus 17 h over square root of Hertz, if you want to go down, you have to improve everything. Yeah.
Does curvature mean the curvature of the wavefronts?
Yeah, if you take this beam, here you consider that each photon gets a kick along the optical link, but since there is a curvature, an atom that is not exactly on the optical axis will get a kick and an effect because of that, and they consider it. So now, gravity gradient noise, so Newtonian noise. So that's the state of the art, obviously, you know better than me, for gravitational wave detection. So optical interferometer, in a Michelson configuration. So they rely on measuring the propagation time between probe masses that are down with mirrors, bulky mirrors suspended. And this is the sensitivity curve for LIGO. I want to concentrate on the limitations at low frequency. So what really builds up a wall there are several effects. Seismic noise, essentially, due to the fact that these mirrors are suspended, and so really close to DC, finally, they feel the movement. There is a noise that enters because of suspensions. Again, it's linked to the fact that there are these suspensions, and then there is gravity gradients due to movement of nearby moving masses. So with atoms, we see, at least intuitively, that we get rid of this the link constituted by suspension. So atoms are not attached to anything. We throw them along the free fall path, and so there is no coupling. And so this effect is eliminated. And we can also say something for Newtonian noise, because you are not obliged to use two probe masses, but you can use a third one or more, obviously. In this way, you can discriminate between signals that are pure gradients and signals that are not only pure gradients or that have higher momenta. And so here I give the phase between two interferometers is given by a gradient, gravitational wave, plus something determined by the local acceleration. So consider now, for example, a person moving close to this probe mass, could be a mass or a person. It will give a big acceleration or a big effect here and much smaller on the other two. So there is a curvature or higher momentum. And so you clearly discriminate. It's not a gravitational wave. If you don't have the central mass, probe mass, you will just see a differential signal. And so, well, it could be a gradient. We consider a much more complex configuration where we consider not only a third mass, but we consider repetition of the gravity gradiometer several times. So here, for example, you consider 17 gradiometers, space 21 kilometers. And now what happens is that this array of simultaneous, because they have to be simultaneous, gravity gradiometers, they get a signal, each one, because of the gravitational wave that is the same for each one, because we are in the really short, so the distance is not comparable to the wavelength of the gravitational wave. So the signal imprinted on each gravity gradiometer is the same. So when we consider the sum of all these phase differences, it goes linearly with the number of gradiometers. If we consider the Newtonian noise, now what happens strongly depends from the distance between these gravity gradiometers. Suppose just for a while that delta is equal to 0. The gravitational noise will be the same for all the gradiometers. Okay, and then it will build up in the same way as the gravitational wave, linearly. And so you don't get any advantage. But now if you start moving at a certain point, you can exploit the fact that the noise is not correlated anymore. Okay, and then they don't sum linearly but in quadrature, and so they grow like square root of n. And so now you gain like square root of n when you make the signal to noise ratio. And so the signal of the gravitational wave can be increased by square root of n. You can do even more, because Newtonian noise, you can consider it coming from masses fluctuations, movement of masses, and then the fact that masses has to be conserved means that you have at a certain distance correlation, and at a later distance you have anti-correlations. So you can choose a really good spacing in such a way that two successive gradiometers are anti-correlated for the Newtonian noise effect, and so you gain even faster than square root of n. And so what we demonstrated in this article is that if you consider the limit, we just considered noise models we found in the literature for the infrasound noise in black and for seismic noise in blue, the dashed point lines, and we applied this kind of array of gravity gradiometer. We can mitigate the effect of gravity gradient noise by a factor of about 10 in the interesting bandwidth that is around 1 Hz. And it's not an optimized configuration, it's just the first trial we did. Now we are working on that. And now I reach the part that concerns the experiment that we are trying to build in this location in France, so not far from here. That's the LSBB, so the Laboratoire Souterrain Bas Bruit, so low noise underground laboratory. So it's a lab that exploits a former nuclear facility during the Cold War. French, they installed their nukes on the high part of the mountain there. They had 45 nukes there, and the control center was down in the mountain, shielded by rock. And so here we can see, for example, one of the remaining silos, and then the control room, and this is the side of the mountain where there is the entrance. The control room is there, and there are already 5 kilometers of tunnels there. The environment is really good to make quite a lot of physics. There are biophysics, geology, geophysics, hydrology, possibly atom interferometry next, for a bunch of reasons. So from the seismic point of view, it's a really good environment, not always, by the way, but you see here It's just, I think, 1 month of data. We are really close to the Peterson noise model. And this is a long term, so 100 hours of measurement. So comparison with other sites, I think that they are all more or less underground, or anyway good seismic sites. Comparison done with a measurement realized with superconducting gravimeters. So LSBB, it's the one pink here. So it's one of the best. So I would say there is just the one in Iran that is slightly better. This is the plot or the map of the tunnels in the gallery in the mountain. So the entrance is here. That's the control room. There are 5 kilometers of tunnels that enters below the mountain. So the mountain is going up along this direction. And our experiment will be located in this part. The tunnels are not yet present. We are working to get them done. And they should be in this configuration, an orthogonal configuration of 2 tunnels. It was 300 meters. Now, because of budget reasons and much more complex stories, they will be probably 150 meters each. But anyway, this is an artistic view of what it should be. So there will be 2 long tunnels that will be equipped with vacuum pipes of roughly 50 centimeters. And the target of the experiment is twofold. So there is one that concerns gravitational wave physics. So we want to do a demonstrator for gravitational wave detection with atom interferometry. I say demonstrator because, as we'll see, the sensitivity will be of the order of 10 to minus 13 at 1 Hertz. So not good enough, obviously, to see gravitational waves. The second target is geoscience. So the experiment will have really high sensitivity in terms of measurement of gravity and gravity gradients, and with that there are already plans to measure, for example, water percolating in the mountain, or there is a water basin underground. Want to see the filling of this basin, and so on. So the boring of the tunnels is planned to start in September 2018 and should be finished for next summer, and the setup should be installed at the end for the end of next year. In the vacuum pipe that will be put in one of the 2 galleries, because for budget reason we cannot equip the second one, we will install 3 atomic sensors, so 1 each on the 2 sides and 1 at the center, as I said before, in order to discriminate between gradients and something that has higher momentum. I designed 2 optical links, one on top of the other, and now I explain why. Consider now to look at these optical links on the front side. Here we have the atoms, and we launch them vertically with a small angle. Will be clear why in a while. So we launch them up. Here there are 2 optical links. For now they are off, and so what happens? Just a parabola. So like a stone, the atoms, they fly and they fall. Now let's turn on the laser at the top at the right time and for the right interval to make a pi pulse. Pi pulse is the mirror, okay? So now you launch your cloud of atoms, and when they reach the top, 0 vertical velocity, you turn on the laser and you bounce the atoms back, because you are making a mirror. So you invert the velocity from plus h bar k to minus h bar k, okay? Because of the interaction with the 2 photons. And now you see what happens if I turn on also the laser below. When the atoms go up along the blue trajectory, they are split with the pi over 2. And so now we have 2 different parts of the wave function that goes up till the top of the parabola. At the apogee, they are reversed and they are recombined where they were split at the beginning. And so finally I add the 2 output ports, and I have to count, as usual, number of particles here and number of particles there. I get the phase, and I know what's the acceleration at this position along the optical link, so an horizontal acceleration. So now some slides about the experiment. So the experiment is designed to be modular. So this is the atomic source. We have a 2D mod loading a 3D mod. There is a launching system to launch in a moving molasses. As I said yesterday, we change the frequency and the atoms are shoot up. There is a preparation region to define the internal and the external degrees of freedom, and then the atoms reach the upper vacuum pipe, where there are the two optical links that are used, as I said, to split and recombine the wave function. This is how it looks like. We have the first prototype in Bordeaux. This is a magnetic shield. Looks messy, but we plan to use it. So we are using it right now in a single sensor configuration in order to test atom interferometer in an horizontal cavity or two cavities. And then we are also building a two sensor configuration to have a gradiometer. There is not the third, but it will be also in Bordeaux, and it will be used like a testing platform for the final underground experiment. We'll test procedure and part of the experiment there before sending them to the underground lab. And here, the bad note. So sensitivity, as I said, is 2 × 10⁻13 in terms of h, or square root of Earth. So not good at all to see gravitational wave, but it is a demonstrator. It's the first experiment really targeting this field in atom interferometry. So the configuration, 150 meter, 2 h/k separation, 1 milliradian detection noise. So really standard configuration, something that is exactly the same as one of the first interferometers done in the 90s by Steve Chu. So it's really a low level, I would say, atom interferometer. So there is space to quickly go down in sensitivity by implementing several techniques of which I speak a little bit. So but you can increase the separation. That's not targeted at the underground lab there, because we have problems already doing 100 meters. So I don't imagine what it will mean doing 10 kilometers, even mentioning to CNRS. But it's possible, for example, to implement large momentum separation, so increase linearly the phase imprinting by 2 to 1000, for example, or increase the number of atoms, entangle the atoms in order to get a boost via squeezing, and so on. So it's reasonably feasible to gain 5 orders of magnitude in a bunch of years, let's say. In order to do it, once the experiment will be working, let's say in 2020-21 at this level, we are working in parallel at several other activities that can be seen like upgrades, future possible upgrades for the underground lab. So we are working, for example, on substituting the 2-photon transition with single-photon transition. We are working in order to increase interrogation time by using trap configuration or repeated coherent interrogation of quantum states. We are working to boost the sensitivity with large momentum splitting or spin squeezing. Colleagues at CERT are working in order to make interleaved, so launching several, like Alberto did this morning, so juggling atoms in this configuration. So they did already with 4 or 5, I think, but in principle you can do with many more. And so we'll have simultaneously several interrogations slightly displacing time, and so on. But the real problem with the experiment in the underground lab is gravity gradient noise. As you see, so we can improve sensitivity, that would be great, but at a certain point we will find this wall. Okay? For this reason, we started studying the effect of Newtonian noise in that site, because till now, or till a few months ago, we just rely on models we found in the literature. This is a question? That's the separation between the interferometers. Okay, so in our configuration, the distance between this one and this one. Okay, the length of the optical link, essentially. Okay. So we started studying the site in order to understand what is going on there. So what we did was to, in the first measurement campaign 2 months ago, we installed a microbarometer to measure pressure fluctuations on top of the mountains and inside, more or less where the experiment will work. So there are no tunnels yet, and so we just went in a tunnel that is existing nearby. And we did a differential measurement there. We studied what's the noise up and down in the mountain. And we studied also seismic noise, because there is a network, a well-developed network of seismometer on site there. This is what we measure in a, don't remember, I think it was a 4 or 5 days campaign. So seismic spectrum is rather close to the low Patterson noise model, except that this frequency band around 1 Hertz, and that's because of the, I don't remember if it's the Mediterranean or the ocean, it was, there were a lot of waves in one of the two, I don't remember which one. They have different frequency, one is at 0.6 and the other one a few, but I don't remember which one is which. For the pressure spectrum, it's not really good. We are close or even above the Bowman model, but anyways, what we measure, that's inside the galleries. What we did next was to convert this noise spectra in equivalent strain. So to do it, we consider seismic spectrum as a superposition of Rayleigh waves and pressure spectrum as a superposition of sound waves. And we consider the density variation in the surrounding medium that determines this kind of spectra. In this way, it was then possible to calculate the strain, the effective strain induced on hypothetic interferometers placed on this optical link. And what we got is here. That's for seismic and that's for atmospheric. As we see, we will not be limited by Newtonian noise for quite a long time. We will be closer to atmospheric gravity gradient noise. See, there is more or less 1 order of magnitude. But what happens is that we could, so what we would like to see, if it's feasible, is to make a long campaign in order to go down, so integrate the signal for a long time and statistically see this noise. I think that I'm not at all an expert. I think that I should ask to someone here. But the idea is to try to make the equivalent of the search of continuous, not continuous, the stochastic background. Okay, so that's noise, and we can see the RMS effect if we make a really long measurement. And anyway, it will be the atmospheric limiting at the beginning, Mega. So we are in this time we are making a longer measurement campaign now for this noise variation on site in order to understand better what we have in that underground lab, and to study it and see how we can finally implement optimized measurement protocols and detector geometries for gravitational for gravity gradient noise reduction, the scheme that I presented before with the array of gravimeter, so in order to optimize the length and the distance within this gravimeter. I finished with MIGA. I have to mention that it's not the unique experiment trying to make a demonstration of gravitational wave detection without interferometry. There are at least two. One is a 10-meter fountain in Stanford, so they proposed first to use interferometers to make this kind of search. And then there is another one. I just there was a 10-minute presentation early in July at the Marcel Grossman conference in Rome. So there is a Chinese group in Wuhan that is has been financed, they said, to build Zyga, it's called. It will be an underground triangle of 1 kilometer for now, but later of 3 kilometers at the beginning, so right end of this year or beginning of next year. They are already financed to make the first triangle and this exploratory 2 more kilometer gallery. And then, yeah, so there is competition, which is good. Now, what's the target in terms of bandwidth? So here, I took the graph from the gravitational wave plotter online, and I added in red the window that is the target one for atom interferometry. It goes, let's say, from 10 millihertz to a few hertz. So it's a window that is really interesting, as the group in Birmingham, so Ilya, Mandel, Alberto, and the other Alberto mentioned and described in this paper, recent paper. where they build up a case for a DCS gravitational wave detector. And well, one can read the article to find why it's interesting, but in the abstract they speak of possibility to see signal from type 1a supernova progenitors, mergers in the presence of third bodies. We had the demo this morning. Intermediate mass black holes, seeds of massive black holes, improve sky localization and tracking of population before giving the relay to LIGO and Virgo. For this possibility, there is a recent article from Peter Graham and Sang-Hoon Yang, where they consider a possible terrestrial configuration or satellite one based on atom interferometry in the bandwidth, as usual, between a few tens of millihertz, a few hertz, and they consider what one could have had in terms of signal for the events already detected that you know better than me. And so they study that case. The idea is to fill the gap between LISA and LIGO, so between the space-based interferometer and the ground-based optical interferometers. As I said, and as the article of Alberto pointed out, there is a lot of science that can be done there. There are possibility to track this line before they enter in the bandwidth of LIGO. There is a possibility to detect events that will never reach that side, and more and more. So that's the last, I would say, short part of the presentation. I want just to open a little bit the horizon, and instead of giving just the possibility of atom interferometry for gravitational wave detection, I want to give other possible scheme based on atomic physics. Okay, so there are mentioned here optical lattice clocks. They are more or less atom interferometer, or better, they are atom interferometers. Time and transfer links and Bci resonators. So atomic clocks, I don't know if anyone is aware of what it is. It's rather simple. So you have a classical oscillator producing a continuous signal. Okay, can be a laser, for example, is a ticking, or a microwave source, a quartz. Okay, this oscillator is typically pretty good at short time, really short time. But if you look at its frequency now and in 10 seconds or in 1 year, it's not the same. It's not an absolute oscillator. It's drifting. And so what is done, to make an atomic clock is to periodically tune its frequency, comparing it to the ticking of something that doesn't drift. Okay, an atomic or a molecular system. How is done this tuning? So you periodically make an interrogation. You use this oscillation in some way to probe, for example, the spacing between two levels. That's a frequency. And how you do it? Pivot to pulse, you wait a while. So with a pivot to pulse, you create a superposition between the two states. So you start with an atom in the low level of a two-level system. Here, you implement a pivot to pulse, and after this pivot to pulse, the same as we spoke a lot of time during the talk, we have this wave function. So the atom is at the same time here and there, with an amplitude of probability 1 over square root of 2, and there is also a relative phase between the two, and this relative phase is evolving at a frequency that is given by the energy spacing of these two. So you initialize this system, and this system starts turning pretty fast. Can be, if it is cesium, is 9.2 gigahertz. If it is a strontium clock, is hundreds of terahertz, and so on. But it's turning fast. Slightly after, you close interrogation, and essentially you are looking if your classical oscillator is drifting or not with respect to this absolute frequency. You get an error signal, and you correct the frequency of your local oscillator. Just, for example, in a quartz, you change the temperature, or you squeeze it a little bit. With a laser, you change the current supply, or you act on a piezo or an AOM, or there are a lot of technical ways to implement a frequency change of this oscillator. And that's an atomic clock. That's a plot of the evolution of stability of atomic clocks. The first they enter the scene after the Second World War, 1950. That's the evolution of cesium clock that defines nowadays after the 70s the time, international time, and it goes down pretty fast. And at a certain point, optical transition enter the field, and they quickly catch up, and they are now performing better in absolute terms with respect to the time defined by cesium or microwave clocks. The reason is really simple. You are splitting time with a frequency that is 9.2 gigahertz or hundreds of terahertz. So you have a much finer spacing, okay? Now there are discussions to make the transition from this definition of the second to the definition based on optical clocks. Now this graph ends in 2010, more or less. Now we are already below 10 to minus 18, okay? So they are progressing more and more. And nuclear clocks based on nuclear transition promise to go even beyond. They are speaking of 10 to minus 20, 10 to minus 21. They already identify a few transitions that could be good in order to go down in terms of sensitivity, but also stability, because that's the problem. And nuclear transitions are in principle good, because the nucleus is shielded, but all the electrons are around, okay? This our modern optical clock looks like. You have a laser that constitutes the classical oscillator. This laser is locked, frequency locked, to an optical cavity. So indeed your classical oscillator in the system is this subset, so laser plus cavity. It has a really good short-term stability. It drifts a long time, but periodically is used to manipulate the atoms and get an error signal. And so you are comparing this frequency with the frequency of the atomic system. This for ytterbium, but it's the same as for strontium, and you get this shape for the signal. That's the line width of your laser, that is nowadays of the order of well, that one is pretty wide. The best recorded one is 20 milliards. So how is possible with a clock to measure a gravitational wave? A really simple picture. It turns out that it's really, really similar to an atom interferometer. And by the way, they are in some way the same. There is even an article that describes how the two visions are finally a single vision. So now you have two clocks, one in 0, one in L, and you send a pulse that initializes first this clock when the photons reaches this position, and at a later time the other clock, okay? This pulse that initializes the clock has its intrinsic noise, phase and frequency noise, but is imprinted in the same way in the two clocks. And so you have the noise here, epsilon 1 and epsilon 1, that is the same on the clock on the right. Time passes, and when you close the interrogation, is the same interrogation that I put here. You start the system, you wait some time, and then you compare the frequency evolution of your oscillator with respect to the atomic one. And at a later time, you close this interrogation. And what do you have? Again, you will find that time t passed. You will find an effect of the noise imprinted here as epsilon 1, and you will get an effect of as epsilon 2. On the right side, you will get exactly the same, because again, the same photon interact first here and the later time there with the same noise. Now, if there is a gravitational wave, its effect is of changing. So suppose that it's increasing h between here and there. There is an effective longer distance at a later time. And so what happens is that the time that you read out on the clock on the right is not anymore the same as here, but is bigger by an amount that is h multiplied by L over C. Yeah. And this is a configuration proposed by a group in Gila, Junyi, in order to make an hypothetical satellite-based atomic clock-based gravitational wave detector. So essentially there are two satellites with atomic clocks, one here and one there on each satellite, and optical links connecting the two and comparing essentially time passing seen by optical clock A and by optical clock B. Here there is a scheme of how it looks like the satellite. There are the atoms held in a lattice that is a free-falling lattice, because this lattice is created with a retroreflection of a beam done by a mirror that is attached on a free-falling mass. And then the light stabilized on this system is compared with the light coming from the other one. So it's compared the relative phase, and so you get the difference of time passing here and time there, and you keep measuring and you see if there is a oscillation of this time stability. So they consider 5 10 to the 10 meter distance between the two satellites, so comparable in some way to LISA, and this will give a maximum for the sensitivity at 3 milliards. Lines of the laser is 20 milliards, but will not limit, as I just said, the measurement, because that laser is used both on the atoms in B and in the atoms on A, and then is common mode rejected, and so the measurement will be limited by the intrinsic line width of the atoms used, so the optical transition, which is of the order of 1 milliard. And so if we consider the smallest detectable fractional frequency difference here, we get down to values that are compatible with a detection of gravitational wave, 10 to minus 20 over square root of Earth. And here they were considering rather optimistic numbers. Let's say nowadays they run these optical clocks with a little bit less than 10 to the 6 atoms. They consider an order of magnitude more of atoms. Line width, that's good, and that's a frequency transition. They went on proposing a lot of configuration in order to show that, as I presented before for atom interferometer, you can change via software the sequence of pulses and the configuration of the clock in order to change the sensitivity to different frequencies. You can go from the red curve to the red one, and you can even have this resonant mode that peak the sensitivity at specific frequency, and so it's really tunable, and that way you can go with some sort of same sensitivity from 3 milliards up to a few hertz. Then you can use optical clock in time and frequency so in distribute. So nowadays the signal, the really precise ticking of optical clocks is distributed over large distances, typically of the order of tens or hundreds of kilometers. So the best reported, I think, that is the optical link between München and PTB, so 920 kilometers up and down, so almost 2,000 kilometers. And what happens? How can you transfer the good stability that you have for a clock here at another position? You put the light on a fiber and you had it at the other end. Obviously, that signal picks up a lot of noise because of temperature variation along the fiber, stress along the fiber, so seismic, and there is a lot of effect by reference of the fiber, and so there are a lot of effects that put a lot of noise on that fiber. But now, what did they find out? So what they implemented is that you send the light, but you partially send it back. Okay? So now, this light is sent back and forth, and it takes some time, obviously, to make the round trip. And so to go from point A to point B, it takes L over C, twice this time to come back. And now you can do anything for time shorter than the round trip time because of causality. But for time longer of this, you can implement correction schemes. And how do you do it? For example, consider a round trip time of 1 millisecond. At the second time scale, or 10 seconds, or 100 seconds, the noise that the light picks up going there and coming back is the same. And so when you measure phase shift at a specific frequency that is lower with respect to the round trip frequency, you can just assume that 1/2 is due to the trip in one direction and 1/2 to the other, and that you can apply on this AOM a correction of 1/2 of that phase in order to have at the end of the fiber there the same signal that you have here, and it works pretty well. So they could demonstrate that you can transfer the stability of a clock from here to there better than the intrinsic noise of the laser of the clock. So the clocks at 1 second nowadays, they are at 10 to minus 16 at 1 second. But they demonstrated that the differential stability of the clock here and of its replica there can be as good as 10 to minus 18 at 1 second at hundreds of kilometers. And they integrated it down 10 to the 4 seconds, you get 2 orders of magnitude 10 to minus 20. You can do this trick. So that's the delay time for the path to go from here to there for frequency below 1/4 of this delay time. So you take the noise that you have in the fiber and you can really correct to the intrinsic noise. What can really, well, I don't know what is the background, but it's really low. So they propose to use this kind of optical links to transfer the stability of a clock at large distances in order to implement giant gyroscopes. That's Stefan Schiller in Berlin, with sensitivities that are potentially really high. That's just a proposal. And they realize that using deep underground links probably will even increase the stability of these devices because of lower noise level at the depart. In a really good recent paper, they demonstrated that you can use these meteorological links over a few tens of kilometers in order to detect earthquakes. So it is a plot that in some way can show the potential of these techniques, because this is the plot of all the fibers, not all the fibers, the main fiber links exist in the world to transfer internet data. So there are hundreds of thousands of kilometers of potential meteorological link. Nowadays they are not meteorological because nobody transfer a clock signal on them. But they did an optical link, one in UK, short 10-20 kilometers to make a trial, and then one between Sicily and Malta, I think, a few tens of kilometers. And they could show that so their target was not to transfer the clock from, let's say, Sicily to Malta, and so they didn't use the clock there, but they just closed the fiber on itself in order to send it back and measure the two-way noise and compensate for it. So they didn't really compensate, they just measure it. And they could see that when there is an earthquake, they can detect it because the earthquake just squeezes a little bit the fiber and they have an effect on the round trip time. Not all the fiber used for internet are now they use for meteorological links, just a few of them. But in France, for example, there is a project that is an Equipex like MIGA, the project which I'm working. And now we are entering also on the other one for some reasons. And their target is to distribute the signal of the optical clocks running in Paris at CIRT in all France. So there is this circle, some parts are already implemented, and for mid of 2019 it should be operating. There are other projects in other European countries. So I think that the German French link is already operative. This one is already operative with PTB and München. This one here is operating. This one is ongoing, I think. But at a certain time there will be a continental scale meteorological link that could be used possibly for gravitational wave detection. That's the question that I'd like to answer probably in the coming time. So it's just an idea for now that came out when Bruce visited Bordeaux, and we went to visit a company that is working at several amplifier, bidirectional amplifier for the signal, because to transfer a signal at 1.5 micron from here, for example, down to Bordeaux or Marseille, you have to amplify and re-amplify several times with a really good phase coherence. And so we went to visit this company, and so we then start chatting about possible exploitation of this kind of setup. And the idea for now is just an idea. It's just you have several links, and you could see if it's possible to, so you will get a lot of noise in each of these links independently, but this noise could be really well uncorrelated. So the noise due to vibrations, temperature, mechanical stress, or effect due to fibers should be correlated at a certain point. And then maybe it's possible to dig out the noise and find the effect of a gravitational wave that should be correlated, for example, between link 1 and link 2, and it should be anti-correlated between link 1 and link 3. So the task seems not easy, because that is spectral noise density demonstrated so far over a few hundred kilometers of meteorological link, 0.1 radians per square root of Hertz. If we consider h of 10 to minus 20 at 1 Hertz over 1,000 kilometer link, it will give 10 to minus 14 meters, which means 10 to 8 times smaller than the wavelength of optical photons. This is probably 1 order of magnitude less, so let's say there are 7 order of magnitude so the noise is 7 order of magnitude buried in noise, gravitational wave signal. Last thing is a Bci Resonator. So there is a group that proposed to use BCs in order to detect gravitational waves in more or less the same, so for what I understood, in more or less the same way as Weber proposed to use Weber bars in order to do the detection. So Weber bars are big cylinders with sharp mechanical resonances, and they want to see an excitation of this resonance by a passing gravitational wave. Which are the features of Weber bar? So there is a high mass, they are meter length, they are cooled to, I think, liquid nitrogen nowadays, or I don't know exactly, and then there is a sensitive piezoelectric readout. Speed of sound here is of the order of a few hundred of meters per second, which gives, on the meter length scale, a few kilohertz resonance, okay, for the sensitivity. So the peak sensitivity, the resonance sensitivity is at the kilohertz level. If we now consider BC is much smaller, as I presented yesterday, you can go down to a few micrometer, so micrometer level, but it's a quantum device. You can go down to very low temperature, much lower with respect to liquid nitrogen. It has tunable compressibility. You can make it really, really stiff using advanced technique like Fenchbach resonances. There is a very slow speed of sound, can be as low as millimeters per second, that on a few micrometer gives again more or less resonances in the band between 10 to the 4 and 10 to the 5 Hertz. So it's finally comparable to what they were trying to find, and they are still nowadays trying to find with these kind of devices. And a big advantage is that there are quantum metrology techniques for the readout. You don't rely on classical devices. So the proposal in this paper by Isabel Fuentes tried to propose to use a BC in an atom box. And so going back to what we were saying yesterday, so this is a BC in an atom box, and its shape and its profile looks like the potential, so in an inverted box. And she wanted to use an atom box with a homogeneous potential in order to have a constant speed of sound, in order to get some amplification by resonance. So the eventual resonance is excited by the gravitational wave will just travel, bounce, and build up with time. And so for what it means, she said that one has to prepare an atomic state in a squeeze 2 photon modes, omega n and omega n, and then gravitational wave will produce phonons, which are perturbation in the density profile of this BC at a frequency that is the sum of these 2 phonons. I'm not really an expert of what they are. And then one has to read out the final phonon state. If there is a gravitational wave, you found these phonons, which is perturbation on the profile of the BC. We would like to study this configuration because we found out that I didn't put the slide, but we have an experiment that could make a proof of concept experiment to see if this is feasible or not. It's an experiment of atoms in a cavity, and so we have the advantage that we'll not read out a phonon state. It's something that has never been done so far, a squeezed 2 phonon mode. But we'll use a squeeze atomic mode and squeeze light for the readout, something that is well understood and implemented. And the target bandwidth, as I said, is 10 to the 3, 10 to the 5 Hertz. That's a sketch of the experiment that we have in the lab. So it's a cavity. It's 10 centimeter, the spacing between the mirrors. They are horizontal. And we can make a conservative potential that looks like this. We trap atoms here at the center. And we can make, that's just a theoretical proposal, an atom box there at the center using the higher modes of the cavity, details. And we are working in order to see if it's possible to prepare highly entangled states that could be useful to see the passage of this gravitational wave. And but for now, it's just an idea, also this one. Yeah, with this, I think that, yeah, I finished. This is just technical details on how we plan to produce a atom box. But there are a few minutes, probably it's better to leave time for some questions. Okay, so yeah, okay, just a conclusion slide. That's the take-home message. I try to convince you that cold atoms are a really cool tool to make fundamental physics and potentially to make gravitational wave detection one day. So for now, we have just proposals. But time is passing, and now we are also entering the build-up phase. So a part of the proposal, we are trying to dig the holes. Will be in the coming time. So I presented what we are doing in this underground lab. I presented how we plan to mitigate the really killing effect of Newtonian noise on Earth, and then, well, some ideas of what could be seen if one day there will really be an atom interferometer based gravitational wave detector that will fill the gap between space-based and ground-based gravitational wave detector based on optical interferometers. And finally, I give some ideas of other approaches to gravitational wave detection based on atomic physics. And that's all. I just want to present a little bit collaborators. We had 2 experiments in Bordeaux and underground in Rostrel, past members and some collaborations there. And all the members of the MIGA collaborations that I cannot mention because there are many. Yeah. But there are at least logos. So this scheme of absorbing, so a good sensor of to absorb and emit photons, for sure it is. I have to admit that I don't really understand just because of my ignorance. So the scheme that you propose. No, it's just that I don't know what gravitons are, and so that's my.
My concern is the cross section.
Yeah, if you have photons, you can make a good sensor to detect photons for sure. Yeah. But you have a.
The cross section of the gravitons interacting would be very, very small. That's really, I think that's to me the problem. I mean, if you want a graviton to interact with your system, you have to wait a long time. You have strong
Long means. Long means how long?
40 orders of magnitude longer than you have to wait for a photon to interact. And the point is, the cross section for photons to interact with your atoms is fairly high. The graviton cross section will be very small.
But long means much longer than, for example, 10 seconds.
Longer than the universe.
Ah, okay, no, okay, no. Okay, okay, okay.
Cosmin, you had a question?
You mean this one? Cavity QD. You mean here? Yeah, here we like to see if it's possible to exploit our experiment that is designed to do something else. So is this slide. We designed it to study self-ordering phenomena, completely a different field. But it turns out that we could see if it's possible to implement what they proposed. Okay?
Another question? Another question?
Okay. Now I understand what. Yeah, it's on the other. Yeah, yeah. With vortices in a BC. Yeah. Okay. I understand what you propose. Yeah. I don't have the numbers in mind because I never work on that subject, but they are for sure in the literature because they really change. So they steer the BC with two lasers. Essentially, they kick it. So they turn it. They put a torsion on it, and they see that they change the steering, and they produce one at a certain point, and then two, and then so they exactly know how much you have to steer the BC in order to. This is not squids. This is really a BC, and you just make it turn. You make it turn. Okay, squid is a different device. Yeah.
I want to ask two questions. First of all, are there, I mean, you're building an experiment in France, a sort of prototype NIGA. Are there any other experiments like that being done anywhere else? I mean, for example, this Kasevich group at Stanford seems to be very active, and a lot of ideas have come from other people. Is there anybody else building a prototype like that?
So the other Chinese, they just presented this. It's just a quick, really quick presentation, 5 minutes in Rome a few weeks ago, and so
It's an idea, or they're actually building it?
they got the money. They said to dig 3 kilometers. So it's a triangle of 1 kilometer of side, and also this 3 kilometers because in 3 or 4 years they will get also the money if this one looks promising. They will go on to make a 3 kilometers configuration. So 1 order of magnitude more than what we are doing, by the way. and along each one is a LISA, the first LISA configuration like. Okay, so they will put gravity gradiometers along each arm of the, and then there is of course Kasevich, so he gave most of the ideas of this of most of what I presented. So yeah, they by the way they have
But these 10-meter atomic fountains, are they just a single fountain, or are they actually placed and then interrogated in such a way you can use them as detectors?
no, it's a single one, but they can launch different clouds in it. Okay, they have a bunch of proposals for satellites configuration. I think I have in some slides at the end. Most recent one, yeah, it's the very last slide. They call it a Magis collaboration. So it's this article here. And sensitivity curves is what I presented before. They have the, let's say, the broadband configuration, the standard one with a single loop, and then the multi-loop one that can go down and dig, and to see resonances, to be resonant at a given frequency. And here's how it looks like. It's a two satellite configuration. Here there are all the numbers. There is an atomic interferometer here, atomic interferometer there, and then the parabolic mirrors in order to transfer the light and build the optical link between the two. And yeah, I think they are not financed, but there are a lot of proposals. Yeah, finance, there is our Chinese now, and well, the 10 meter is working. 10 meter will not be enough, most probably, but to make proof of concept, yes.
So the last thing I want to make is a comment. So I always enjoy trying to speculate about what the future is going to look like. And for example, the first measurements of the speed of light were made. Was it in Paris? Who made these measurements? Was this in the?
I would say that the first measurement of speed of light has been done in Florence by Galileo.
Okay.
He went on the mountain and with lamps, and he concluded that speed of light is infinite of higher than what he can measure. So
Okay, the first measurements that actually got the correct value were, I mean, and when I was an undergraduate, for example, we did experiments in the lab where we measured the speed of light by just adding some extra phase lines, some phase layout on an oscilloscope, right? We measure the speed of light, and we did a lot of measurements, for example, which were 100 years or 150 years earlier than state of the art. They were simple to make. So I think it's likely that a few hundred years from now, physics students will build gravitational wave detectors as laboratory experiments, and they'll probably build them using these techniques. That's my guess.
have to live long.
You go